Hello, once again, BC students. We're going to continue our discussion on 9.5, alternating series, by taking a look at example 1b. Always been a fan of this particular example because of the fact that it's not so obvious maybe that this is an alternating series to begin with, because we don't see the typical negative 1 raised to the n or n plus 1. We have this negative 2 to the n minus 1 in the denominator, and it really requires that we do a slight adjustment to this expression to get it to look more like one of these two forms. And there's a couple of different ways to do this, and I want to go ahead and address both ways because the shorter version, the shortcut, may not be so obvious to everyone initially. Hopefully after this demonstration it will be. But what I was going to suggest is taking a look at the terms of the series and seeing if we can get a handle about what's going on with them. And that can be easily accomplished by just starting with n equal 1 and deciding what your nth term a sub n expression would be. So if n were to be 1, we would obviously have 1 in the numerator, and then negative 2 to the 1 minus 1 is negative 2 to the 0 power, which anything to the 0 power, of course, is 1. Moving on to let n equal 2, we have 2 in the numerator, and the denominator would be negative 2 raised to the 1 power, or in this case negative 2. And you're going to see I'm very reluctant to reduce any of these fractions because I think it's going to kind of prove my point here in just a little bit, and hopefully you starting to feel a little at ease the fact that this does seem to alternate. At least it's doing so after 2 terms. Continuing on with n being 3, we would have 3 in the numerator, and negative 2 squared would be positive 4 in the denominator. Let's go to the 4th term, 4 on top, negative 2 cubed, which of course is negative 8. Moving on to the 5th term, we would have 5 over negative 2 to the 4th. That would be positive 16, wouldn't it? Now let's do one more. Let's let n equal 6. 6 in the numerator, negative 2 to the 5th power is negative 32. So there you have it. I've got 6 different fractions, all of them in an unreduced form if they were to reduce in the first place. And from this, I think that you can start to get a little feel for how you might want to rewrite this. So, let's take a look at this summation expression from n going 1 to infinity. Does it indeed alternate? Well, of course it does. It alternates in such a way that the first term is positive, then the second term is negative, third term positive, etc. So that would take on the appearance of the negative 1 raised to the n plus 1. Now you could also say n minus 1. There's nothing wrong with that. I'm going to always stick with an n plus 1 exponent when I want the even numbered terms to alternate. Okay, so we've got the alternating sign taken care of. What else do we see that's in common from one term to the next? Well, they're each a fraction. Well, that's pretty easy. Draw a fraction line. All right, let's look at the numerator. What do we notice? The numerator is 1 for the first term, 2 for the second term, 3 for the third term. Looks like that numerator would be an n. Now the denominator would be about the only thing that's of some challenge here, but if you take a look, you go from a 1 to a 2 to a 4 to an 8. Seems like we're powering up a base of 2. Now we just have to get the exponent to be correct. Now be real careful, because I don't think we can say that it's 2 to the n, because that would make 2 squared 4, or 3 squared 9, or I'm sorry, 2 to the third 8 for the third position. That's not quite where we're at. If you take a look, our exponent is just off by 1. So let's see if we just subtract 1 from the exponent, and let's test it for n equal 4. 2 to the 4 minus 1, or 2 cubed, would match that 8. And you can see that works on for so on and so forth. So we've got an nth term expression that looks a lot more like one of our 2 over here in the Theorem 9.14 box. Now I know some of you are probably sitting there watching this thinking, hello, couldn't you just factor out a negative 1 and use the exponent n plus 1? Yes, of course, that would work. And in the future, if you want to exercise that shortcut, by all means do so. But I just don't think that that's always so obvious to most students. And I think you can never fail with writing out a few terms and seeing what's going on. Okay, now we're set to go ahead and do our alternating series test. I'm going to go ahead and start that and put that over here on the left side. Criteria 1. Well, let's check it out. Does the limit as n approach infinity of the portion of our nth term that doesn't contain the negative 1 to the n plus 1, so that would be the portion underlined here, does this limit equal 0? Well, it's a good question. Does that equal 0? Maybe it's not so obvious. Now, again, intuitively, you can look at this and you can start plugging in values of n and compare the top with the bottom. And, of course, I think that you'll come to the conclusion that the bottom, 2 to the n minus 1, does grow faster than the numerator n. But if that isn't so obvious to you and you try to attack this by plugging in infinity and get the indeterminate form infinity over infinity, we always understand that there's an option for that result, and that's called L'Hopital's rule. So if we go ahead and take the derivative of the top and the bottom, we would get 1. Now the derivative of this denominator is a little tricky. You don't do this a whole lot in BC. You're going to start doing it more and more. It's a technique that you learned last year in Calc AB, but the derivative of 2 to the n minus 1 is the natural log of 2 times 2 to the n minus 1 power. Now once you've arrived at this step, it's pretty clear that by the time n becomes infinity, the bottom grows without bound, and you would have 0 as a result. So, criteria 1 has been met. We are sort of on our way to convergence, possibly. We just have to verify that criteria 2 is met. And once again, there's a couple of different ways that you can do this. I'm not opposed to you trying to rewrite the expression with an a sub n plus 1 look to it and compare it with a sub n. You're going to find out in this one it's a little tricky. In fact, I'll write this, let me switch colors to make this a little bit more obvious. Let's say if we let the n change to n plus 1, and I'm looking at this guy right here. So the top would become n plus 1. The denominator would be 2 to the n minus 1. Well, I'm going to change this n to an n plus 1, so doesn't that make the 1 sort of cancel? So I would have 2 to the n. Now, just to recap, once again, I'm just basically taking n out and replacing it with n plus 1 to try to get this sort of nth term expression written. And then I'm questioning whether or not that would be less than or equal to the original nth term expression, which is n over 2n to the minus 1. Now, I see this as pretty tricky. Even if you cross multiply, I don't think it becomes very obvious that the left side is indeed smaller than the right side. So remember what I said before, this condition 2, basically all that it's saying is that this particular sequence, a sub n, is decreasing. And we can show that by just using the first derivative test. So once again, let's let the function f of x represent the nth term expression x over 2 to the x minus 1. And let's see what the first derivative test is going to do here. You're going to have to use the quotient rule. So the derivative of the top times the bottom minus the top. Whoops. Yeah, minus the top. Okay, now we're going to take the derivative of the bottom. So that would be the natural log of 2 times 2 to the x minus 1. And we just divide that all by 2 to the x minus 1 all squared. Okay, now if I do a little simplification here, I notice that in the numerator I'm going to have the ability to factor out a 2 to the x minus 1 power. Now upon doing that, I'm going to be left with 1 minus x times the natural log of 2. And then my denominator will just stay as it is. Well, let's start thinking about this. Remember, we're dealing with values of n or values of x. They're interchangeable now that I've made this declaration, that are 1 and higher. Now, if you take a look at that, what does that say about the different components of this particular derivative? Well, this right here, the 2 to the x minus 1, for any x that's 1 or bigger, is guaranteed to be a positive number. Right? Even if you let x be 1, you'd have 2 to the 0, which is 1. 1's positive. Now, you really don't have to look very closely at what's going on in the denominator, because the exponent here pretty much tells the story, right? The exponent squared means you're always going to be dealing with a positive value in the denominator, so we're good here. So really, the only thing that really needs to be looked at is the 1 minus x times the natural log of 2 for values of x that are 1 and bigger. Well, since the natural log of 2 is going to already be, well, natural log of 2, if you think about that, that's actually a value that's less than 1, I believe, because you've got to have a value here that's at least e or larger to be 1 or bigger. So, okay, we're less than 1 there. But as you keep growing with your x, going to 2 to 3 to 4, it should become pretty obvious that this guy is going to end up taking on a negative value, because x times the ln of 2 will be larger than 1. In fact, it's going to begin when x is 2. So you could say that f prime of x is indeed less than 0. I don't want to say for all x, because that's not really true, but I could say it for x greater than or equal to 2. So we have established the fact that we sort of achieve that decreasing characteristic with our a sub n, so criteria 2 has been met. So if criteria 1 and 2 are both met, we can go ahead and make the declaration that we have a series that converges. And that takes care of example 1b.